Okay, pre-calc, we're going to start the next chapter. This is our last chapter that we're going to do this year, and it should be some review because it's on sequences and series, and we did some sequences and series last year. So you should know some of this. So we're going to start with what a sequence is. A sequence is a set of numbers with a particular pattern. And each number in the sequence is called a term. So we have some different kinds of sequences. We have a finite sequence, which means it's a sequence with a limited number of terms. It ends. So an example would be 1, 2, 3, 4, 5. That's a sequence with a limited number of terms, and then of course an infinite sequence is a sequence with an unlimited number of terms. Okay, an example of that would be 0, 1, 2, 3, 4, 5, ... which is actually the set of whole numbers. It has no end. Okay, it's an infinite sequence. It just keeps going on forever and it never ends. So let's look at term notation. The first term in a sequence is denoted by A1. And each subsequent term is denoted by an plus 1, where n plus 1 is the term number. In the sequence. So here's an example. Suppose we're given a sequence here, 2, 5, 8, 11, 14, ... Okay, A1 equals the first term. This number right here is the term number. So it is 2. A5 equals the fifth term. Okay, the fifth term. Here's 1, 2, 3, 4, 5. There's the fifth term. So A5 is 14, A8, and A14. In order to find those, we're going to have to find more terms of the sequence. So we're going to have to look at the sequence and decide what's happening here. How do we find the next term? We're going to add 3 each time to get the next term. So the next terms here, 14 plus 3 is 17, then 20, then 23, then 26, 29, 32, 35, 38, and 41. So the 8th term is 1, 2, 3, 4, 5, 6, 7, 8, 23, and the 14th term, 8, 9, 10, 11, 12, 13, 14, whoops, my 1 went away, 41 is the 14th term. So that's what those little numbers mean on the bottom. And this next part here, it says, since each term value is paired with exactly one term number. Okay, this is paired with this, 2, 1, and 2 here, 5 and 14, 8 and 23, 14, 41. Since each number is termed with exactly one term value is paired with exactly one term number, it means that the sequence is a function. So if we draw a little chart here where we have n, which is the term number, that's down here, 1, 2, 3, 4, 5, and we have an, which is the term value for this, for this sequence up here. The first term is 2, the second term is 5, the third term is 8, the fourth term is 11, and the fifth term is 14. So we can say that this right here is a function like an xy function, except an NaN function, and the domain is the set of term numbers, which are these right here, and the range is the set of term values, which are these right here. So in an infinite set, or an infinite sequence, the domain is the set of natural numbers. Because the domain is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, on and on and on and on. Good. Let's look at the next part. Recursive formula. Okay, a recursive formula is, lots of definitions in this section, a rule in which, in which one or more previous terms are used to generate the next term. Okay, a recursive formula is a rule in which one or more previous terms are used to generate the next term. So an example of this is the Fibonacci sequence. And the Fibonacci sequence is 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. So in this sequence, we can say we're going to define A1 equals 0, A2 equals 1, and AN equals AN minus 1 plus AN minus 2. Because the way you get the third term is by adding the first term and the second term. So we're going to say 0 plus 1 equals 1. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13 equals 21. 13 plus 21 equals 34, and so on. That's what this is saying right here. We're adding the two terms right before it. So if we wanted A3, we would add A3 minus 1 plus A3 minus 2, which is 3 minus 1 is 2, and 3 minus 1 is 1. So to get the third term, we're adding the first term and the second term. To get the fourth term, we would add A3 plus A2. So to get the fourth term, we add the second and the third. You always add the two right before it. In order to use a recursive formula like this, we had to define what A1 and A2 are, and we would probably say, this is the formula for n greater than or equal to 3. Because we can't use this formula for A2 or A1. We had to actually define it. So let's look at some examples. Example 1, it says give the first 5 terms of each sequence. So we've got A1 equals 25, and AN equals AN minus 1 minus 7 for n greater than or equal to 2. That's what I was just talking about, where you can only use this for the second term and higher. You can't use it for the first term. That's why the first term is defined. So A1 equals 25, that's defined. A2 equals A2 minus 1 minus 7. What is 2 minus 1? A1 minus 7, which is 25 minus 7, which is 18. A3 is A3 minus 1 minus 7, which is A2 minus 7. So we're going to you always take the 1 before it and subtract off 7. A4 is A4 minus 1 minus 7, which is A3 minus 7, which is 11 minus 7. And A5, it asked you for 5 of them. It's A4 minus 7, which is -3. So the first 5 terms of this sequence are 25, 18, 11, 4, -3. And the pattern is you always take the 1 before it. This means the 1 before it, and subtract 7. So that's how you're doing this here. Don't make it harder than it is. All right, let's look at number 2. You don't have to write it all out like that I did. If you can see the pattern, I'm just writing that so that you know where those numbers came from. So we got A1 equals -2, and AN equals 3 times AN minus 1 plus 1 for n greater than or equal to 2. Again, this is because we've defined A1, so we can only use this equation for the second term on up. So let's find our 5 terms. A1 equals -2. A2 equals 3, make that better, 3 times A2 minus 1 plus 1. Okay, I'm substituting a 2 in for these n's for the second term. So 2 minus 1 is 1. But what does A1 equal? A1 equals -2. So this is 3 times -2 plus 1, which is -5. Then for the third term, we're going to do 3 times A3 minus 1 plus 1. And what is A2? A2 is -5. So we're going to do 3 times -5 plus 1, and that equals -14. So then you can see the pattern that it's just 3 times the term before it plus 1. So to find the other 2, you don't have to write those all out. You can just do 3 times the term before it plus 1. That's going to be -41. And this one, 3 times the term before it plus 1 equals negative 122. So the first 5 terms are negative 2, negative 5, negative 14, negative 41, and negative 122. And those are the 5 terms. Okay, that's a recursive. Oh, there's more recursive formulas. So let's look at these. Number 3, we've got A1 equals 40 and AN equals 1/2 AN minus 1 plus AN minus 1 for n greater than or equal to 2. So we've got our first term, and then our second term is going to be 1/2 the term right before it plus the term right before it. So that is 20 plus 40, which equals 60. So for the third term, we're going to take 1/2 the term right before it plus the term right before it, and that is 30 plus 60, which is 90. And then the fourth is 1/2 plus this, and we get 45 plus 90, which is 135. And for the last one, we're going to have 1/2 of this plus 135, and that is 202.5. And those are our first 5 terms. And let's do number 4. We got, okay, number 4 is a little different because it's kind of like the Fibonacci sequence. They're defining A1 as 8, A2 as 10, and AN equals AN minus 1 over AN minus 2. And now it's for n greater than or equal to 3. We can only use this equation right here for the third term on up. But we have our first 2 terms defined. So our third term, now we're going to take a 3 and substitute it in for these n's. And we're going to get A 3 minus 1 over A 3 minus 2. 3 minus 1 is 2, and 3 minus 2 is 1. So look at this. It's A2, which is the term right before it, over A1, which is 2 terms right before it, and that equals 5/4. Okay, so the fourth term is going to be the term right before it, which is 5/4. I'm going to run out of space. And the term 2 terms before it, yeah, let me put it over here. A4 is the term right before it, which is 5/4 over 2 terms, 10. And remember, that is 5/4 times the reciprocal of that, which is 1/10. And 5 goes into there too. So A4 is 1/8. And then the last one is the term right before it, which is 1/8, over the 2 terms before it, which was A3, which was 5/4. So this equals 1/8 times the reciprocal, which is 4/5. 4 goes into there too, and that is 1/10. So our first 5 terms are 8, 10, 5/4, 1/8, and 1/10. All right, now comes the tricky part. What if you're given a sequence and you have to write the rule? All right, so here's our sequence. And it says to write a recursive rule. So, and then find A8. So a recursive rule means you're going to use some of the terms before it. You're going to see that we have a different kind of rule called an explicit rule, which comes next. And you can do, for a lot of sequences, you can do either way or both. But right now we're going to look for a recursive rule. So we're going to define A1 to be 9. When you're doing a recursive rule, you always have to at least define the first one. All right, and let's see what's happening here. Well, we got, what's one good thing to try is seeing what the difference is. What's the difference between 9 and 13? Plus 4. What about this one? Plus 4. What about this one? Plus 4. Oh, look at that. The difference is always adding 4 to the one before it. So a good recursive rule would be a n minus 1, take the term right before it, and add 4. And for n greater than or equal to 2, because we have to define what a1 is. And that's our answer. So to find the 8th term, we're going to have to keep going. We've got 1, 2, 3, 4, 5. So we're going to have to keep going, and we'll have 29, 33, and 37. Change color on me. 1, 2, 3, 4, 5, 6, 7, 8. So A8 is 37 for this one. All right, that one wasn't too hard. Now let's look at number 6. For some of these, I'm just going to tell you, just try your best and see what you can come up with. They're not always easy to see, and there's not anything that I can just tell you, this is what you do. You just have to kind of look at it. Now, let's look at the difference between number 6 and number 5. If you see number 5, the numbers are going up very slowly. Here in number 6, the numbers are going up much quicker, which tells you that probably there's some kind of multiplication involved. So let's see. I'm trying to think of what's the best way to do this. I'm just going to tell you what it is right now, and you're going to see that it would have taken some time to figure it out. We're going to define A1 and A2, and then we're going to say AN equals AN minus 1 plus AN minus 2. So you're going to add the 2 right before it and multiply by 2. And of course, we're going to have to say for n greater than or equal to 3 because we defined both A1 and A2. So if you see this, you're going to add 1 and 3, you get 4 times 2 is 8. 8 plus 3 is 11, times 2 is 22. 8 plus 22 is 30, times 2 is 60, and so on. And if you keep going, I'm just going to tell you, you could figure this out. A8 is 1,224. All right, let's look at an explicit rule or formula and see what the difference is. In an explicit formula, a rule, it's a rule in which the nth term is defined as a function of n. So we're not using terms right before it. We're not going to have things in our formulas like an minus 1 or an minus 2. We're just going to have n's in our formula. So let's look at an example. Number 7. An equals 5n plus 1. So let's write the first 5 terms. Okay, A1 equals 5 times 1 plus 1, which is 6. A2 equals 5 times 2 plus 1, which is 11. A3 equals 5 times 3 plus 1, which is 16. A4 is 21, and A5 is 26. And here are the first 5 terms of that sequence. So you see the difference between an a recursive and an explicit formula. This formula doesn't have any a n minus 1 or n minus 2. It just has n's in it. I think explicit is a little bit easier, but maybe not. Okay, so let's look at number 8. an equals 3/2 to the n minus 1. So a1 equals 3/2 to the 1 minus 1, which is 3/2 to the 0, which is 1. a2 is 3/2 to the 2 minus 1, which is 3/2. a3 is 3/2 to the 3 minus 1, which is 9/4. And you could keep going. a4 is 27/8, and a5 is 81/16. Okay, that's number 8. Let's look at number 9. We've got an equals n minus 1 over n plus 2. So a1 is 1 minus 1 over 1 plus 2, which is 0 over 3, which is 0. a2 is 2 minus 1 over 2 plus 2, which is 1/4. a3 is 3 minus 1 over 3 plus 2, which is 2/5. a4 is 4 minus 1 over 4 plus 2, which is 3/6, which is 1/2. And a5 is 5 minus 1 over 5 plus 2, which is 4/7. And the last one here, number 10, an equals the square root of 3n. So a1 equals the square root of 3 times 1, which is square root of 3. a2 equals the square root of 3 times 2, which is square root of 6. a3 equals the square root of 3 times 3, which is the square root of 9, which is 3. a4 equals the square root of 3 times 4, which is the square root of 12, which is 2 times the square root of 3. And a5 equals the square root of 3 times 5, which is the square root of 15. And that's, oh, there's more. All right, let's do number 11. We've got an equals n cubed minus n minus 1 squared. So you can see that they can get really complicated. And when you're going this direction, it's not too hard. But if you have some of the numbers and you have to find the rule, it makes it a lot harder. So a1 equals 1 cubed minus 1 minus 1 squared. Well, that of course is 0, so that's just 1. a2 equals 2 cubed minus 2 minus 1 squared. Now it's just going to be 1. That's going to be 8 minus 1, which is 7. a3 is 3 cubed minus 3 minus 1 squared, which is 27. 3 minus 1 is 2. 2 squared is 4. So that's 23. a4 is 4 cubed minus 4 minus 1 squared. So that's going to be 64 minus 9, which is 55. a5 is 5 cubed minus 5 minus 1 squared. I don't have that all figured out. I just know it's 109. All right, and the last one, oh, a factorial. Remember factorial? We've got an equals n factorial minus 4. So A1 is 1 factorial minus 4, which is 1 minus 4, negative 3. A2 is 2 factorial minus 4, which is 2 minus 4, or negative 2. A3 is 3 factorial minus 4. Okay, remember what 3 factorial is? That's 3 times 2 times 1. So that's 6 minus 4, which is 2. A4, 4 factorial. So it's going to be this 6 times 4. It's going to be 24 minus 4. So it's 20. And A5 is 5 factorial minus 4. You can do that on your calculator. It's 116. All right, that's going this direction. Now let's see going the other direction. Number 13, we have to write the explicit rule. So let's see what we got. We got 4, 7, 10, 13, 16. And we got to look at that and decide, oh, I wrote the wrong one down. I wrote the run underneath it. Okay, let me get the right one. Number 13 is 1, 4, 9, 16, 25, ... Do any of these numbers look familiar? They're all squareds, right? This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So we can write this an equals n squared. And then it asks you to find A25. One good thing about an explicit formula like this is we don't have to write them all out to find the 25th. We can just substitute 25 in for n, and we get 25 squared, which is 625. All right, and let's look at the next one. Number 14, we've got 9, 11, 13, 15, 17. Now this one, you should notice, is going up much slower than the one that we just did. So when it's going up slow, you should look at differences. What's the difference between this? 2, 2, 2, 2. So we can just say an equals, so the difference is 2. So we can say, but we can't just say it's the term before plus 2 because we're not doing a recursive. We have to think of how can we get this number out of a 1? So, oh, this is hard. We're going to have formulas for special kinds of sequences, and it's going to be way easier. But the answer here is just 2n plus 7. And sometimes there's lots of different ways that you can do it, right? There's not only one right way. So this right here is why this is a 2. So if we said 2 times 1 is 2, and what do we have to do to that 2 to get 9? We have to add 7. So, and for n equal 2, 2 times 2 is 4. What do we have to do to 4 to get 11? We have to add 7. So that's where that comes from. And then to find A25, we would just do 2 times 25 plus 7, and that equals 57. All right, so the last two on here, we're going to write an explicit and a recursive formula to show you how you can do either one sometimes. So this section today is just sequences in general. As we go on, we're going to look at some specific sequences. All right, so for explicit is when we're using n. If we look at this, sequence, it's not going up very fast. So let's look at the difference. Plus 3, plus 3, plus 3, plus 3. So we're going to say an equals 3n. We're going to put 3n because this is a 3. And what do we have to do to this 3n to get a 4? We have to add a 1. So that's going to be our explicit formula here. And our recursive, we're going to use the term before it. So we're going to define a1, and then we're going to say an equals the term before it plus 3 for n greater than or equal to 2. So there's recursive, and here's explicit. Okay, not too bad. Let's look at 16, the last one, and then you can try some for homework. 1/2, 1, 3/2, 2, 5/2, ... All right, so what do you notice here? Well, there's a couple things you can notice. If you look at the difference between here, it's plus 1/2. Do you agree? So with the same way we did explicit up here, if we say the explicit is going to be an equals 1/2 n, and what do we have to do to this to get this? Nothing. It's just 1/2 n. When n equals 1, we get a half. When n equals 2, we get 1. When n equals 3, we get 3/2. When n equals 4, we get 2, and so on. So there's our explicit. And our recursive, what do we have to do? We have to define a1, and the next term is going to be the term right before it plus 1/2 for n greater than or equal to 2. And that's the answer. All right, so you can try some of these for homework, and I will attach the homework and tell you what you need to do on it. And then next week we'll get into it more.